truly rare to find a piece of enterprise software that teams across the business actually want to use more as the company grows.
It's a very specific secret sauce.
It is. And today we're focusing on a platform that seems to have found it, Snowflake. But here's the question. What happens when all that enthusiasm, all that scaling, turns into just a staggering data liability?
That is the core challenge we're tackling today. As companies put everything from sales pipelines, proprietary algorithms, customer PII onto a single cloud data platform, the security strategy has to evolve just as fast. We have to move beyond just thinking, how fast can we query this data, and start building a really robust, defensible structure around that immense liability.
Okay, let's unpack that a little. Our sources really highlight that the value of a platform like Snowflake comes from, connecting real and customer needs, the stuff sales and support teams hear every single day, and feeding that back to the technical teams.
Right. It's a feedback loop.
Exactly. And that loop lets the product evolve in a way that meets those unique customer needs at scale. It's that willingness to build for the enterprise, not just sell to it, that makes it so sticky.
And it creates this powerful, virtuous cycle. We are right in the middle of this information age transformation, and the sheer volume of data is just overwhelming.
I mean, it's everywhere.
It is. Snowflake first got critical notice around, 2016? Mostly because its architecture solved these massive query performance issues that plagued all the legacy systems.
But since then,
data generation has just exploded. We're talking billions of IoT devices, millions of applications constantly generating and feeding information into the system.
and it really is a self-feeding beast, isn't it? The accessibility of modern data science tools means that using this data isn't just for a tiny specialized data team anymore.
Not at all.
More people across the entire organization are empowered to use it, find insights, and get value from it. And of course, every time someone finds value, it just encourages the organization to collect even more data. It just fuels the whole cycle.
Precisely. You can take the example of a travel booking company. They're pulling in all their core internal data, order history, search patterns, what reviews people submit.
All the basics.
And then they're enriching that with these vast third-party data streams. This huge unified data set becomes the engine for everything, predicting personalized offers to maximize revenue, helping HR predict attrition.
Or even customer success predicting churn risk.
Exactly. And when that critical mass of corporate knowledge is all in one place, it becomes this immense, almost irresistible target if it isn't secured methodically.
And that data growth, it often speeds up the risk through this fragmentation problem, the organizational issue that we all know as shadow IT.
Fragmentation is a huge risk accelerator. Whenever the technological fabric of the enterprise starts to fray, the likelihood of error, of data corruption, misuse, or even theft just goes way up.
Right.
And shadow IT tends to pop up in departments that need to move fast. Think marketing, finance, customer service. It's often created by really smart, motivated people who subscribe to that engineering mantra.
Move quickly and break things.
Right. Move quickly and break things.
And that's fine, I guess, until the tool they built to scratch that immediate itch just gets orphaned. What happens when that script, the one written 6 months ago for some urgent analysis, is just forgotten? The person who wrote it leaves the company.
But the system, the key, the permissions they defined in the shadows, they're all still active. They're still holding access to sensitive data. That is an enormous, forgotten liability.
And that brings us to, I think, a really necessary reality check on breaches. When we prepare for a data leak, we often think about the spectacular, the Mission Impossible scenario.
Right. The super sophisticated threat actor maybe rappelling into a data center to steal encrypted hard drives.
It's a fun mental image, but it's not the day-to-day reality, is it?
Not at all. Our sources confirm that while those high-level attacks exist, most attacks exploit the simplest, weakest link in your defenses. We are talking about non-technical administrative missteps.
Like what?
Employees reusing simple passwords across multiple platforms, overly permissive access rights that were just never revoked after a project ended, or, and this is the crucial one, those forgotten old credentials left unattended for that urgent script.
So that's kind of a good news, bad news scenario. The bad news is we keep making these simple mistakes. But the good news is because the weakest links are so often administrative or policy-based or procedural, there are clear, straightforward, and relatively simple steps that organizations can take right now to drastically reduce their risk.
Absolutely. The effort to impact ratio for addressing those foundational administrative risks is extremely high.
So our mission today in this deep dive is to provide you, the listener, with that actionable, logical framework, a precise playbook for securing your data on Snowflake. We are going to specifically differentiate between what Snowflake handles out of the box, what you must configure yourself, and what requires additional external controls.
Yeah.
Let's move immediately into securing the platform foundation itself.
Okay, so the Snowflake story, it really starts with a fundamental architectural choice. When the company was founded back in 2012 by Mike Speiser, Benoit Dageville, Marcin Zukowski, and Thierry Courons, their goal was, well, revolutionary.
Which was what?
Eliminate the multi-million-dollar cost and the operational pain of owning dedicated legacy data infrastructure.
The old model forced a really painful choice, right? If you wanted more storage capacity, you had to add these expensive new servers that came packaged with both storage and computing power. You couldn't scale one without the other.
Exactly. Snowflake they broke that paradigm. Their core insight was that storage capacity and computing power do not have to expand at the same rate. By leveraging the immense, the elastic power of the public cloud, and they support AWS, Azure, and GCP, they allowed organizations to provision storage completely independently of computing power. This is what made scaling a data solution radically more cost-effective.
And that also fixed the problem of the peak workload, which used to be a massive headache and expense.
Yes, exactly. Think about end-of-quarter financial reconciliation or that massive weekly risk analysis report. In the old world, you had two choices.
Right.
You either buy a massive, expensive data warehouse that sat idle 90% of the time just to handle that one peak hour, or you manually stop all other crucial data processing just to run the big job.
Neither is a good option.
Not at all. Snowflake lets you spin up these massive virtual warehouses' compute power only when that peak workload hits, use it, and then tear it right back down, paying only for the use. This flexibility is why it fits the modern explosive data collection demands so perfectly.
Now, when we talk security, because Snowflake is delivered as software as a service, a SaaS product, it does fundamentally reduce the security surface that you're responsible for.
It does.
But as we established, it certainly doesn't eliminate it. This is the shared responsibility model in action.
And in that shared responsibility model, you have to know precisely where your liability begins and where it ends.
Yeah.
Our sources categorize the security surface into three essential layers. The first layer is what's handled out of the box by Snowflake, or the underlying cloud provider. Think of physical security, the data centers, base encryption standards, that sort of thing.
Which is great, but we can't just start there.
No, absolutely not. The second layer is what's provided by Snowflake, but must be configured by you, the customer. This is the critical zone.
And this includes things like
Identity integration via single sign-on, defining granular network policies, configuring roles, and access control. If you skip this configuration, you are just dangerously overexposed.
And the third layer.
The third layer requires additional customer tools or controls things like application-level encryption or maybe third-party governance layers to enforce custom policies that aren't native to the platform.
So when an organization is moving to Snowflake, one of the earliest structural decisions they face is the organizational architecture. Do we go with a single account or a multi-account strategy?
From a pure operational simplicity standpoint, the single account is definitely the easiest path. You only have to define users, roles, and monitoring once. The management overhead is minimal.
But if security is the top priority, the sources are really strong on this. They recommend the multi-account approach, despite that friction.
Absolutely. The strong separation you get from a multi-account strategy, say, one account for production, one for staging, and a separate one for highly regulated data is a massive security gain.
How so?
Well, it prevents, for instance, a bug in your staging environment from ever impacting the liability of your production environment. If one account is compromised, the blast radius is contained.
But that friction point, the management overhead, that was always the issue. Provisioning and managing new accounts used to be a huge manual headache, especially as companies scaled.
It was, but that friction has been deliberately addressed by Snowflake. They introduced what's called the org-admin role, which gives administrators the ability to automate the provisioning, modification, or even deletion of accounts across the entire organization.
Can you give us an example of how that automation actually changes the workflow?
Certainly. Before, setting up a new staging account might involve a multi-day process with support tickets and manual credential exchanges. A real pain.
I can imagine.
Now, if ACME Candies needs a new staging environment in a specific region, an administrator can just run a simple create account command. They specify the edition, the region, admin credentials, and the whole process is automated, audit logged, and near instant. The org admin role basically lets you scale your security architecture without that exponential administrative cost.
Which makes that multi-account strategy much more feasible.
Okay, let's look at deployment choices, because these fundamentally change your security baseline, especially for highly regulated industries dealing with standards like TIBO or FedRAMP.
Right. So the standard deployment is the default, and it's a multi-tenant environment. This means the load balancer, the metadata store, the cloud services, they're all shared with other Snowflake tenants within that cloud provider's virtual private cloud, or VPC.
The connection to the VPC is secure over HTTPS. But here's the key risk that you need to pay attention to. Data is not encrypted between the virtual warehouse, the compute layer, and the storage bucket within that VPC boundary.
So if there were a highly sophisticated attack that managed to intercept traffic inside the cloud provider's network, the data would be exposed in transit.
That is the risk you accept at the standard level. It's an extremely low probability event, but it exists. To mitigate this and to meet compliance standards like IPay, you move up to the Business Critical Edition.
And what does that do?
This edition automatically encrypts data within the VPC, closing that internal transit risk. And critically, Business Critical also introduces the capability for Tri-Secret Secure, which allows you to manage your own encryption keys.
And what if an organization has, say, zero tolerance for multi-tenancy, like a major government contractor or a financial institution?
Then you opt for the Virtual Private Snowflake, or VPS. This is the highest level of isolation you can get. The customer is moved into a dedicated, isolated VPC. The entire virtual network services compute storage is dedicated solely to you.
It completely removes that multi-tenant risk.
Entirely. It's a significant operational commitment and cost increase. But for heavily regulated environments, it's non-negotiable. And it's also worth briefly mentioning Private Link, which gives you a direct, secure connection from your own on-prem network, or VPC, directly to Snowflake, bypassing the public internet.
That progression standard, Business Critical VPS, it gives a really clear path based on your risk tolerance. Before we leave this foundational layer, we have to discuss the time bomb, historical data persistence. Data you thought you deleted might still be there, and it still carries security and compliance liability.
This is critical because compliance regulations don't care about your operational workflow. They just care about where the data physically resides. And there are 4 distinct ways historical data persists that you have to monitor.
Let's start with stage data.
Right. Stage data is the area where you temporarily put files, CSV, JSON, whatever, for ingestion into Snowflake, or where files land when you export them.
Okay.
Even after the data is successfully loaded into your table and the table itself is cleaned up, the original source files might still be sitting in that stage area, which is usually an S3 bucket or an Azure container. You must have policies to aggressively monitor and delete these files. Otherwise, you just have sensitive files left unattended in a cloud storage bucket.
The second area is backups.
Internal or external backups are a separate, distinct liability. Organizations need clear policies on where backups are stored, who can access them, and how that access is logged and audited.
And the sources warn against a specific practice here.
They do. They strongly warn against creating internal backups, which just means copying data within your Snowflake account to a different database simply for archival purposes. This almost inevitably leads to orphaned, ungoverned data sets with sensitive PII that nobody remembers even exists.
The third persistence method is a fan-favorite feature that can become a compliance nightmare: time travel.
Time travel is brilliant for data recovery and operational agility. You can undo a destructive action with the undrop table command, or you can query data from a specific point in the past using a simple SQL offset. For example, select from table at offset igmas 600 shows you the table exactly as it was 1 hour ago.
But here is the massive security implication, especially when it comes to privacy laws.
Correct. GDPR's right to be forgotten, or similar clauses in CCPA, means that when a customer demands their information be deleted, it has to be irretrievably gone. The ability to pull deleted information using time travel, even 90 days later, might violate those requirements.
So what's the mitigation?
You have to ensure you set very short retention periods, from 1 day up to 90 days, depending on your plan on any tables containing sensitive PII. You have to align your time travel policies with your legal requirements, not just operational convenience.
And finally, the last persistence method is the absolute worst-case scenario: fail-safe.
Failsafe is essentially an emergency cord managed by Snowflake support. It offers up to 7 days of restoration time after your time travel retention period is fully expired. It's expensive, it's not guaranteed for immediate retrieval, and it's meant for catastrophic scenarios. Organizations should actively avoid relying on failsafe as part of their standard recovery plan.
Okay, that is a comprehensive look at the foundation. Let's shift our focus entirely to Chapter 3. Data protection via encryption and key management. We need to look at protecting data both when it's moving and when it's just sitting still.
Starting with data. In transit, this is all about defending against man-in-the-middle, or MITM, attacks. When your analyst hits run on a query, that data travels across numerous networks, your local ISP, global carriers, public cloud networks, to reach the Snowflake service. An attacker tries to eavesdrop or modify that data as it travels.
So the standard defense mechanism here, transport layer security, is just non-negotiable.
Absolutely. Snowflake enforces transport layer security, TLS, by default for all communication, and non-encrypted communications are simply rejected. This is, table stakes in modern security. It ensures that even if traffic is intercepted, the underlying data remains cryptographically protected.
Now, for the more complex part, data at rest. How does Snowflake manage the keys that protect the massive volume of data stored in tables? Our sources describe a hierarchical key model.
Right. The best way to think of this is like a set of Russian nesting dolls of protection.
Yeah.
A flat key structure, one master key protecting everything, is simple, but it's dangerous. If that one key is compromised, all your data is lost. A hierarchical model adds resilience and isolation.
How does that hierarchy actually work?
So we have 3 levels. At the very innermost level, you have level 1, file keys. These are used to encrypt the individual data files stored in the cloud storage buckets. These keys are ephemeral and there are a lot of them.
And what protects those file keys?
That's level 2. Table master keys. Each table in your schema has its own master key, and that key is used specifically to encrypt the hundreds or thousands of file keys associated with that single table.
Okay, so file keys are protected by table keys. What protects the table keys?
Finally, the table keys themselves are protected by the account master keys, which are securely stored and managed in a hardware security module, or HSM.
So to decrypt a single data file, Snowflake has to progressively unwrap that hierarchy. Use the HSM protected account key to decrypt the table key, use the table key to decrypt the file key, and then use the file key to decrypt the actual data.
Precisely. It makes a bulk compromise exponentially harder. And because keys are the target, Snowflake has really robust measures around the key lifecycle. The account and table master keys are automatically rotated when they're more than 30 days old.
And what about old data, say files that were encrypted with a key that was retired years ago?
That's where periodic rekeying comes in. This is a feature that automatically runs in the background to re-encrypt older table files, the ones encrypted with retired keys from over a year ago, using the latest, most current security standards. It's a proactive measure against the possibility that an old key might eventually be compromised with future technology.
This whole structure sounds very efficient, but for organizations handling extremely sensitive data or facing strict compliance mandates, they often demand control over the root key. That moves us into the realm of Tri-Secret Secure.
Tri-Secret Secure is where you, the customer, get the ultimate control over data processing. In this configuration, you generate your own root key using your cloud provider's key management service, or KMS. This customer-generated root key then combines with Snowflake's HSM key and a third internal key to form the composed account master key.
Wait, if the key is composed of the customer's root key, what's the profound implication there?
It means that your data cannot be decrypted, processed, or even queried without your explicit approval to access that root key in your KMS. You hold the proverbial kill switch.
A kill switch.
Yes. If, for any reason, you perceive a breach or an unauthorized access attempt, you can immediately revoke access to your root key, which effectively stops all data processing activity on your account. Snowflake cannot access the data without that key component.
That is immense control, but it also sounds like immense operational responsibility. If you mess up your own KMS, you lose access to your data entirely.
That's the core trade-off. You gain the ultimate security control, but you take on the responsibility of ensuring that key is highly available and safely managed. It's a classic example of security maturity. The greater the control you demand, the greater the operational liability you assume.
Beyond Snowflake's native encryption, there's an even deeper layer of protection that some customers attempt, application-level encryption.
This involves encrypting specific, highly sensitive columns before the data is even loaded into Snowflake. Let's go back to ACME Candies. Their HR department stores manager reviews. If they absolutely need to guarantee this text is protected, even if the entire Snowflake key hierarchy is compromised, they'll encrypt that review text column before ingestion.
But the immediate trade-off here is a severe loss of usability.
It paralyzes the data. If the HR manager wants to run a query to find all reviews containing the keyword ILIS %incredible%, the query fails. It's trying to match a clear text word against an encrypted string of ciphertext. You've made the data secure, but you've rendered it nearly useless for analysis.
Which defeats the purpose of centralizing it in the first place. Are there any workarounds to mitigate this functional paralysis?
Yes, but they reintroduce risk. Organizations can use external user-defined functions, or UDFs. UDFs are basically custom pieces of code you write and run inside the database environment. These UDFs can be programmed to call a third-party service that you control to perform decryption during the query process.
So the data is decrypted just long enough to run the query?
Exactly. The caveat is that while the UDF enables the search, clear text data will be processed temporarily by Snowflake as part of the query execution. So application-level encryption should really only be recommended for a very small number of fields where the security requirement utterly outweighs the functionality trade-off.
That's a great distillation of the encryption layers. Let's transition now to Chapter 4, authentication. If encryption is the defense around the lockbox, authentication is the guard at the gate.
Right. And when we talk about keeping strangers out, we have to first address the weakest link, which is often the default process of local password creation.
This is a crucial administrative vulnerability. When an admin creates a local Snowflake user with the create user command, the password parameter has no policy enforcement at all.
That's the failure point. An admin can literally set the password to ABC or 12345. Our sources stress that the robust password policy requiring 8 characters, a digit, uppercase, etc., only applies after the user's first login.
So there's this window of risk.
A completely unprotected window where a weak admin-set password is valid and vulnerable. It's the equivalent of handing someone a bank vault key that says password engraved on it.
So if an organization absolutely must use local users, what's the mandatory mitigation?
2 simple steps. First, enforce the must-change password true parameter, forcing the user to change it upon first login. Second, and this shouldn't need saying, but it does, the admin should still set an initially strong password. Don't take unnecessary risks in that short window.
But the real security goal is to just eliminate this local weakness entirely by outsourcing identity management.
Absolutely. The moment you integrate an identity provider or IDP like Okta or Azure AD for single sign-on, you gain massive security benefits. It enforces your organization-wide MFA and strong password policies, and it removes another place, the Snowflake account, where passwords have to be stored and defended.
And when we move from dozens of users to thousands, the administrative burden shifts from passwords to provisioning. That's where SCM comes into play.
SCIM, the System for Cross-Domain Identity Management, is the automation engine. It uses an API to automatically manage user identities and roles across platforms. Think of the headache it eliminates. Manually ensuring that when a new hire joins the marketing ops department, they are correctly granted the marketing OPS role in Snowflake.
SCIM handles that linkage seamlessly.
It does. When a user is added to the Data Science Level 2 group in Okta, SCIM automatically provisions the user, maps the group, and grants the Data Science L2 role in Snowflake. It's essential for scaling securely.
But because SCIM is so powerful, it can create, modify, and delete any user and role. The token it uses is basically a super admin credential.
It must be treated as such.
Yeah.
2 security measures are non-negotiable for SIM. First, you have to assign a network policy to it to guarantee that API calls are only allowed from the trusted networks of your identity provider.
Okay.
Second, you need to rotate that token, ideally every 3 to 6 months, to mitigate the risk of misuse if it's ever inadvertently exposed.
Moving from human users, what about our non-human users? Applications, ETL processes, automated scripts, they definitely shouldn't be using shared passwords.
No, the risk is way too high. The recommended method here is key pair authentication. This uses standard asymmetric cryptography, a private key held by the application and a public key configured in Snowflake. Only an application with the corresponding private key can authenticate.
And what's the security requirement for managing those private keys in a production environment?
Absolute secrecy. Key creation and rotation must be automated and handled securely via enterprise vaults. HashiCorp Vault, AWS Secrets Manager, things like that.
Yeah.
You should never, under any circumstances, allow local copies of the private key on developer laptops or shared drives. If the private key is exposed, that secure channel is instantly compromised.
We also have that middle ground, Human users, like data scientists, running quick ad hoc analysis via Python or SNOSQL scripts. They need to adhere to the organization's SSO and MFA policies, too.
They absolutely do. You achieve this by ensuring the script's connection string uses the authenticator external browser parameter. This forces a federated login, opening a browser window for the user to authenticate via their IDP, ensuring that strong MFA policy is applied even for a quick, one-off analysis.
Finally, before we leave the application layer, we have to address the most famous application vulnerability: SQL injection.
This is a foundational factor in application security, and it typically stems from just lazy programming. If an application takes user input, say a city name, and builds a query using string concatenation, that input can be treated as executable logic.
The classic malicious input being something like Nythrid or 1.
Exactly. When that input hits the application, the query that was supposed to select deals only in NYC is fundamentally changed. The attacker's input changes the logic to select deals in NYC, or where 1 equals 1, which is always true, meaning the query returns all deals across the entire table.
And it can be worse than that.
Oh, much worse. An attacker can use commands like union to pull data from other completely unrelated sensitive tables.
How does a developer accidentally create this risk?
By relying on string concatenation, just literally sticking the user's variable into the SQL command string. The fix is absolute and non-negotiable. Always use parameter binding. Parameter binding ensures the user input is treated only as a value, not as executable SQL logic, shutting down the vulnerability entirely.
That sets a strong boundary on who gets in. Now, Chapter 6, authorization. We've verified the user's identity. Now we dictate what that authorized user can actually see and do. Snowflake uses role-based access control, or RBAC.
Right, and RBAC is the most common model. Users get roles, roles get privileges. The key distinction in Snowflake, though, compared to many other database systems, is that users choose a single active role for each action. They don't just inherit the sum of all permissions from every role they possess at once.
That's a huge operational difference. It forces a user to explicitly adopt a specific restricted role if they are, say, running a report, or explicitly escalate to a higher privilege role for administrative work.
It encourages the principle of least privilege by design. If you're running a simple select query, you should be using your restricted analyst role, even if you also possess the powerful sysadmin role. This separation of duty is key.
Let's break down those built-in administrative roles, because their misuse is where a lot of internal exposure comes from.
At the very top is account admin, the absolute superuser. This role has all privileges, including some that can't be delegated. The hard rule is, never grant this role to another custom role, and never set it as a user's default role. It's reserved only for essential top-level configuration and should be used sparingly.
So how do we achieve separation of duties for day-to-day management?
We use the lower administrative roles. User admin is restricted strictly to creating and managing users in custom roles. Security admin manages all grants to objects who can access what. And then you have sysadmin, which manages objects like databases, tables, and virtual warehouses. By distributing these duties, you minimize insider risk.
A core feature that can either streamline security or lead to catastrophe is role hierarchy.
Role hierarchy allows one role to inherit privileges from another. This is done with a simple command like grant role lister generic to role estralatum. This is incredibly useful for providing common object access.
Right.
It's also great for temporary projects. Create a project Halloween role, grant it to the necessary teams, and when the project ends, revoking the parent role instantly removes access for everyone.
But this introduces the danger that security experts call hierarchy hell. What is that risk?
The risk is opaque inheritance. If you grant role A to role B, and role B unknowingly inherited privileges from a distant role C 5 months ago, you've just inadvertently given users of role A access to data tied to role C that they should never have seen. This deep, complex nesting makes auditing and privilege removal feel like traversing a minefield.
Now we address sensitive data within tables using fine-grained security. We'll start with column-based security, restricting access to sensitive columns like salary or medical data.
The old methods cloning data, or creating complex views for every department, led to stale data and massive maintenance overhead. The modern, highly recommended method is dynamic data masking. This lets you create reusable masking policies that define how data is transformed based on the user's active role.
Give us the ACME Candy's salary example again.
Sure. The organization creates a masking policy that says, replace the salary value with arrow none unless the current role being used is accounting, or HR. That policy is applied directly to the salary column. An analyst running a query gets a column of 6, while the HR manager running the exact same query gets the plain text salary. The key is reusability.
Moving from columns to rows, we have row-based security, which restricts access to specific records within a table essential for multi-tenant applications or regional separation.
This is implemented using row access policies, RAPs. A policy is applied to a table column, perhaps a region column, and it filters the visible rows based on the user's current role. So an analyst using the SDR LATAM role only sees customer records with the LATAM region tag.
What's the major security advantage of RAPs over just using filtered views?
This is a critical point for defense in depth. Row access policies work not just on select queries, but across all DML operations. That's data manipulation, language think, update, delete, and insert. RAPs ensure a user with the SDR LATAM role cannot inadvertently update or delete a record belonging to the SDR US region, providing comprehensive defense.
Finally, let's consider the operational trade-off of self-service access control. This is less about security mechanisms and more about operational efficiency and scale.
As an organization matures and you have thousands of data consumers, data engineers can easily spend all day being human gatekeepers just running rubber stamp grant access commands. The operational trade-off is this. You can build a custom application wrapper, a user interface, that automates the grant and revoke process. A user requests access to Project Halloween data. The application automatically grants them the role temporarily and logs the entire transaction.
That greatly reduces the data engineer overhead and speeds up data availability, but it requires a massive development investment.
It is a significant custom software engineering cost. However, the reward is an audited, transparent data marketplace. Users get what they need faster, and you can automate revocation in the background to ensure temporary access doesn't silently become permanent overprivilege.
That bridge is perfect for our final layer, visibility and monitoring. All these controls, encryption, access policies are useless if you can't verify they're working and detect when they are being circumvented or abused.
This is where Snowflake really stands out compared to many legacy data warehouses. Every single operation, every query run, every object accessed, every login attempt is audited by default. It's stored for up to 1 year, and you don't need to set up storage buckets. This native built-in auditing is a monumental relief for security teams.
And the most incredible part for people who live in the data world is that these audit logs are accessible and queryable via SQL. You don't need to learn a whole new logging platform.
That's right. But teams need to understand the difference between the two main sources of this metadata, Snowflake, .accountisage, and information schema. This distinction is crucial.
Let's start with the real-time data.
That's the information schema. These views and functions give you near real-time monitoring with zero latency. If you need to see who is logging in right now, you use this. However, the retention is short, usually only 7 days to 6 months. It's for operational monitoring.
And for security forensics and long-term compliance.
You turn to Snowflake .accountisage. The data here is delayed, between 45 minutes and 3 hours, but the retention is up to 1 year. Crucially, it contains data on dropped objects. If a malicious user deletes a table, you can still audit that history long after the object is gone, which is vital for any investigation.
Let's get granular on the security monitoring use cases, starting with core access risks.
We need continuous monitoring for anomalies. That means checking the login history views for patterns like excessive failed logins, which can indicate a brute force attempt, or connections from new, unusual IP addresses that are outside your defined network policies.
Then there's the major internal threat vector, admin role abuse.
This is often accidental, born in convenience, but the impact is the same. Separation of duties dictates that admin roles should manage infrastructure, not pull business data. You must query history to find instances of high-level roles, like account admin, being used to run simple select queries on business data. If you see account admin querying the customer PIA table, you have an audit failure.
What about those dangerous historical liabilities we discussed earlier, like files left behind?
We need to proactively find ungoverned stages. You can query the stages view to track stages owned by the public role or old stages that were never deleted. This is how that sensitive CSV file uploaded months ago for a one-off ingestion gets forgotten in an S3 bucket.
And we can audit changes to the security architecture itself using these logs?
Yes. The query history lets you track configuration changes, every alteration to time travel settings, network policies, or any user creation command not issued by the user admin role. And for identity automation, we use the REST event history function to monitor SCIM activity checking for failed provisioning calls or unexpected source IPs.
We've spent all this time locking data down, but modern business requires sharing. Let's transition to secure data sharing. How do we move data out to partners and customers while maintaining control?
The basic approach is the direct share. You create a share object, grant it access to tables or secure views, and specify the consuming account. It's fast and simple.
But what are the key security and operational limitations for you as the data provider?
You get no logging of consumer queries on your side. The consumer's querying your data, but their activity is logged only in their account. You lose visibility. Additionally, shares must be in the same geographic region, which can be a constraint.
To maintain control and share only subsets, we often use secure views to apply filtering logic.
Secure views allow for filtering before the data reaches the consumer. We can use column-level filtering or row-level filtering via dynamic secure views that filter results based on the current account consuming the data. This ensures the supplier only sees the purchase orders relevant to them.
A more advanced approach is sharing functionality, not raw data, using secure user-defined functions, UDFs again.
This is a powerful technique to prevent bulk data extraction. Instead of sharing a table of upcoming discounts, ACME Candies could expose a secure UDF called Get Future Discounts for Product Integer. The consumer must supply a product ID to get a result.
And why is that significantly more secure than sharing the view?
It adds friction. A consumer can't just run one select query to get all the discounts. They would be forced to write a complex script that iterates through every possible product ID, running potentially millions of queries against your warehouse just to scrape the full dataset. It makes abuse significantly more costly and slower.
Here's where the technology gets genuinely fascinating. Secure joins. This allows two separate companies to find overlaps in their data without either company ever exposing their raw customer lists to the other.
This solves a massive business and legal necessity. ACME Candies and ACME Savories want to run a joint campaign targeting customers they both share, but they can't share plaintext customer lists. Secure joins rely on complex cryptography, specifically hashing and salting.
How does that actually work without exposing the plaintext?
They don't exchange the email address directly. Instead, they generate a complex, unique joined key. This key is a hash of the private data item, like the email, combined with the unique account ID hash and a randomized salt key. Both parties use the same complex hashing method, exchange these one-way hash keys, and then join their data based on the matching hash. They discover the overlap without either ever seeing the other's raw customer identifiers.
And when you combine all these controls, secure sharing, UDFs, secure joins, and fine-grained policies, you construct a distributed data clean room.
A clean room is the final layer of compliant data collaboration. It acts as a controlled capsule, ensuring data is accessed only after utilizing these multiple layers of security, enabling sensitive market analysis while strictly adhering to privacy regulations.
And finally, the meta use case, turning the power of Snowflake against itself by using it as a security data lake.
This is a growing trend. Organizations are aggregating logs from dozens of enterprise security controls, firewalls, endpoints, intrusion detection systems into Snowflake. Why? Because of its scalability and the ability to run complex analytical SQL queries on massive volumes of log data, which legacy SIEM systems often struggle with.
And there's an open source framework built specifically for this function.
SnowAlert. Developed by Snowflake's security team, this framework runs scheduled queries on all ingested log data, standardizes the results into actionable alerts, and then sends automated notifications to platforms like Jira or Slack. It transforms raw log volume into targeted security intelligence.
Wow. That was a truly exhaustive journey through the entire security perimeter. Let's synthesize the 5 core layers of this playbook one last time.
We started with the foundation, infrastructure and shared responsibility, defining the necessary isolation multi-account, VPS, and stressing the critical liability of historical data persistence from staged data and time travel.
Then we dove into encryption and key management, detailing the robustness of the hierarchical key model, automated rotation, and the ultimate customer control offered by Tri-Secret Secure, while acknowledging that it shifts operational liability entirely onto you.
Third was identity and authentication, emphasizing the immediate need to move away from weak local passwords towards centralized SSO and MFA, SCM provisioning, and mandating key pair authentication for all automated systems.
Fourth, authorization and access control, where we talked about enforcing the principle of least privilege through RBAC, managing role hierarchy wisely to avoid hierarchy hell, and applying granular controls via dynamic masking and row access policies.
And finally, visibility, leveraging Snowflake's native auditing capability, a monumental volume of operational data available via SQL in both real-time with information schema and long-term forensic views with account usage.
So what does this all mean for you, the individual or the team leader who has to implement this today? It feels like an overwhelming list of tasks.
It is a significant undertaking, and implementing everything at once is impractical. The operational priority must be addressing the foundational risks and implementing basic monitoring first. Address the low-hanging fruit, eliminate weak passwords with SSO, set up basic monitoring for failed logins, and most critically establish policies and checks for unmanaged stages. Tackle those before you embark on complex row-level security.
That is deeply pragmatic advice. We know that the reason platforms like Snowflake exist is to generate value from data, so the pressure for data availability is constant. The strategic challenge is constantly balancing that pressure for utility with the immense liability that data carries.
And this raises the final important question for you to consider moving forward. Knowing the dangers of opaque inheritance and hierarchy hell, how can you design your role architecture today, right now, to maintain explicit transparency and control? The aim is to ensure that future data consumers can get the specific access they need to drive value without inadvertently inheriting privileges they absolutely should not have. That tension between maximum utility and minimum liability is precisely where effective data security strategy truly lives.